In this video, we are going to talk about conformal maps. This is our overview slide, which we'll spend about 5 minutes on before going over each topic in more detail and more examples. The second topic we will cover is mapping of grid lines. So we can study mapping properties by considering how the mapping treats grid lines, that is, a line of constant u and of constant v. So here we have an example that we will go through in our video where our function w is equal to z squared, and we have our constant values of u here, and we look and see how it gets mapped by w. Here we have constant values of v, and we'll look and see how it gets mapped by w. Finally, we'll look at conformal maps, which is a function that preserves angles. That is, a conformal map will map two lines that intersect at some angle into another pair of lines or curves that intersect at the same angle. So it's preservation of angles that makes the mapping conformal. And we will find that all complex functions which are analytic are conformal mapping functions. We have this illustration here. Here we have the W plane with two lines, this blue line and this black line. They meet at the intersection W naught, and the angle between them is this angle alpha. If we map then, using a conformal map onto the Z plane, maybe this blue line becomes a curve, this black line might become a curve. We'll see that it intersects at Z naught, but we'll also see that the angle between the two curves, at this point you have to use the tangent line for the curves, but the angle between the tangent lines will still be alpha. There will be two other topics with conformal mapping that I'll cover in a later video, conformal mapping part 2. This concludes our overview of this video, so we'll go back and take a closer look at mapping complex functions. When we map real numbers, we only need a number line. So we need one axis. The x-axis is where we normally map our real numbers, and again, it's called the number line because we only need the line. But when we map or graph a complex number, we need two axes, one axis for the imaginary part and one axis for the real part. So then when we want to think of a function, we can't graph it as x being the input and y as the output. We need an entire plane to represent the input or the domain, and another entire plane to represent the range. So we have the z plane, which is understood to be complex, the complex plane, and the w plane, which is understood to be complex. And then our mapping takes points from the z plane, and then it maps it to something in the w plane. Our example is wz equals z squared. So writing z in the form of x plus iy, z squared then becomes x squared minus y squared plus I times 2xy. Now when we plug in the point z equals -1 into w, in this case x is equal to -1 and y is equal to 0 because there's no I component. So our final form is 1 squared plus 0 is equal to 1. So that means on this graph, our z equals -1, which is here, I just put it in blue, gets mapped to the point 1, which I highlighted in blue again, from -1 to 1. Next, if we plug in z equals I, that's where x is equal to -1 and y equals 1. Be careful because y is not equal to I, it's equal to 1. Sometimes I make that mistake. So then when we plug it into z, we get 0 squared because x is 0. Our -1 squared, and then our I times 0, so we get -1. That means our point I over here gets mapped to -1. So again, from I in the z plane to -1 in the w plane. If we have the point -I, that's where x is 0, y is equal to -1, then we have our -1 squared plus 0, so we get -1. So -I, which is over here in the z plane, gets mapped to -1, which we already colored blue, but I'll put another little yellow dot inside, so -I to -1. And I'll let you go through the other couple of examples. But the idea is, again, we're mapping from a plane, which is our domain, to another plane, which is our range. a couple of points. If one point in the z-plane maps to only one point in the w-plane, as we had here, each of these points map to only one point in the w-plane. It is true some points mapped sometimes more than one point maps to the w-plane, but each one, when you look at each one individually, they map to exactly one point, and that is called single valued. It is possible for the mapping function to take one point in the z-plane to more than one point in the w-plane, and this type of function is called multi-valued. Examples of multi-valued function would be the logarithm or something like the square root of x or z, because like the square root of 4 can give you positive or negative 2. And in previous classes, we said that when things were multi-valued, we said they were not functions. We just called them, I don't know, equations or something. So functions in other classes had to be single valued. In complex analysis, we don't make that distinction, but we do say that we either have a single valued or a multi-valued function. Our next point is the function wz can be inverted to give a function of w that takes points from the w-plane and maps them back to points in the z-plane. So the inverse here for negative 1, well, negative 1 should map us back to I and negative I. So this would be, the inverse would be an example of a multi-valued function. If we have a function that both wz and its inverse are both single valued, then the mapping between the two complex plane is called one-to-one. Our next topic is of mapping of grid lines. It helps us study the mapping properties. We look at how the mapping treats grid lines or lines of constant value. For an example of using mapping of grid lines, we're going to consider the function w equals z squared and how w equals z squared maps the constant lines u equals negative 2, u equals negative 1, u equals 1, and u equals 2, and the constant lines v equals negative 2, v equals negative 1, v equals 1, and v equals 2. Writing our z as x plus iy, we see that w squared is equal to x squared plus I 2xy minus y squared, which means our u, which is our real part of our complex number, is x squared minus y squared, and our v, which is the imaginary part or the part that gets multiplied by I, is 2xy. And what we see is when u is constant, when we set x squared minus y squared equals c, we get a hyperbola. And when v is a constant, we get 2xy equals c, also a hyperbola. And here I have my graphs. I have my u and v axis in my w plane. I have u equals negative 1, u equals negative 2, u equals 1, and u equals 2. When I map them, u equals 1 is the hyperbola x squared minus y squared equals 1, and that's this hyperbola here and this hyperbola here. It crosses with the x-axis at 1 and negative 1. And I labeled this curve u equals 1 to show you that this curve came from this u equals 1 line. When I do u equals 2, I get this hyperbola here, hits the x-axis at 2 and negative 2, and this hyperbola, or this other half of the hyperbola. And again, I labeled them u equals 2 to indicate they come from the line u equals 2. I think in your book, they labeled the axis, so they labeled this this part of the axis 1 and this part of the axis 2. They're labeling the graph, not the axis. For u equals negative 1, this line then becomes this hyperbola, and u equals 2 becomes this hyperbola. These dotted lines, the gray dotted lines just kind of help me draw the hyperbola. So this is how w equals z squared takes these constant lines, or lines where u is a constant, where the u, the real part of the function, is constant, how it gets mapped over into the z-plane. I can do the same thing now for v is held constant. So that is equations of this form, 2xy equals c, which is also a hyperbola. So I have v equals 1, v equals 2, v equals negative 1, v equals negative 2 in the w plane, and then I map them over. For v equals 1, I get this curve here and this curve here. For v equals 2, I get these two curves. For v equals -1, I have these two curves. I don't know why I have a dotted line here, for no good reason. And then at v equals -2, I have this curve, and this again is in the z-plane. I am going to shrink my graphs and move them up here so I can do something really risky in this spot in my next slide. Actually, it's not risky at all. That was just my attempt at creating excitement. And what I did is I overlaid my U curves, those are the ones in black, with my V curves. And one of the things I'm going to say is if you intersected the U and V graphs, they would intersect at 90-degree angles, right? Because they're on the axis and the axis are at 90-degree angles. So when you look at the intersections of the black and the blue, the U lines and the V lines, they should intersect at 90-degree angles. If they don't, it's a lack of my ability to draw, not the lack of the 90-degree angles. The idea that the angles between the vertical and the horizontal lines are preserved when you map is something called conformal mapping. That's our topic. A conformal map is one that preserves angles. So a conformal map will map two lines that intersect at some angle into another pair of lines that intersect at the same angle. So what I was saying in our previous example, since these vertical lines intersect our horizontal lines at a 90-degree angle, when we combine these two graphs or overlay these two graphs, if I had drawn them well, whenever they intersect, they will intersect also at a 90-degree angle. And this function, w equals z squared, is in fact a conformal mapping. And the idea, again, about the conformal map, when we map from the w plane to the z plane, if we have two lines or two curves, this blue line and this black line, and they intersect and they have an angle between the two lines is alpha, then when we map the blue line and when we map the black line into the z-plane using our function, if it's conformal, that means where the blue and the black line meet, that will have this angle of alpha. It'll preserve the angle. And note the lines are not necessarily straight, like here I drew them curved. So for curved lines, the intersection angle must be defined by local tangents. I have moved my notes about conformal maps here so that we can have room for an example. So we'll look at the function wz equals e to the z, and we know it's conformal because it is analytic throughout the entire z-plane, and by our notes, all complex functions which are analytic are conformal mapping functions. I am going to use this example to illustrate the other two things we covered in this video, which is mapping of the grid lines. So studying this map by looking at how the map treats lines of constant values of u and constant values of v, and then also just verifying some of the angles. So if we look at the angles between constant value u and v, those are 90-degree angles, that those angles are preserved once we use this mapping w equals e to the z. And again, we're not here to prove that it's conformal, we simply use this fact to say it's analytic and therefore conformal. But let's look at wz now. And we write z as x plus iy, then by properties of exponents, that's equal to e to the x, e to the iy. To analyze this, I'm going to pull this information here that we had reviewed in a previous video when we were talking about mappings of complex functions. We talked about translations, rotations, and reflections. The thing I'm interested in right now are rotations. We said that if we had a complex number z, and we multiplied it by e to the I theta prime, because z is equal to r e to the I theta. When we multiply by e to the I theta prime, what happens is our r's here, our e and I remain the same, and our thetas add, just because of the way you multiply exponents. Which means that when you multiply by e to the I theta prime, what happens to your vector, the result is the vector gets rotated counterclockwise by theta prime radians. And what that means for our example is over here when we have wz equals e to the x, e to the iy, well, e to the x is going to be some number, some constant, a scaling, or rather our radius. This e to the iy then is a rotation by y radians. So the e to the iy is responsible for the rotation of the vector. Now I'm going to take a look at our grid lines to see what it means when we're conformal, what happens to these grid lines. Again, I'm not proving that w equals e to the z is conformal. We already know that because complex functions which are analytic are conformal, and e to the z is analytic. But what I wanted to illustrate are these grid lines to get a feel for what the function is doing to the straight lines, and then also looking and seeing how the angles are preserved. So the first line I'm going to consider is z1 equals c1y. That's my alarm, by the way. And this is the line where x is held constant at c1 and y varies. So this looks like x is held constant and y varies, looks like a horizontal line. So this is my line z1. Ignore the lines. It's not really, it's c1 is equal to a random constant, not necessarily 2, and z and y varies. So this is my line z1. z2 is going to be a horizontal line where x varies and c2, y is held constant at z2. Now, if we look at w of z1, that's going to be e to the x, which is e to the c1, e to the iy, and w of z2 is e to the x, e to the iy, which is e to the I, c2. Now, I want to know what happens to z1, and I kind of moved this graph over here. z1. If I look at this, when I map it, I have some radius of e to the c1, and then I have my circle. As y goes from, let's say, 0 to 2 pi, we're going to trace out a circle. So here is what happens to z1. My straight line becomes a circle of radius ec1. Again, it's right here. This is what tells us what happens to the line. Here is the radius again, ec1. The circle comes because y varies. And I said when y goes from 0 to 2 pi, that it'll trace out the circle, but y is going to take all values because here z1 takes all values, so it'll repeatedly trace the circle. But the image is just a circle. Let's look at w of z2. So here's z2, another straight line. They're at 90-degree angles. E to the x, now x varies, so this radius goes from 0 to infinity. And this IC2, now our angle is fixed. So that's this blue line here. We have a fixed angle, and our radius goes from 0 to infinity. So Z1 gets taken to a circle, and all vertical lines get taken to circles of radius e to whatever the C1, the x-axis coordinate is. The horizontal lines now get taken into rays that come from the origin. Looking at the angles, here we have a 90-degree angle. Here, because we have a circle centered around the origin and we have a ray coming out of the origin where they intersect, this is also, taking the tangent line at the circle, you'll have a 90-degree angle. So that's kind of what it is to be conformal, is that you've preserved this 90-degree angle after you've done the mapping. And that's the material for this video, which is a little bit short, but that's okay. We're going to have a continuation, a part 2 video. And to review what we talked about, we reviewed mapping of complex functions, and we looked at, since it takes an entire plane to represent a single complex number because you have the real part on one axis and the imaginary part on the other axis, when you have a function, you need one plane, which usually we denote as the z-plane to be the domain, and a second plane, which we usually denote the w-plane to be the range. We talked about using grid lines, or lines of constant u, or constant v when we're looking in the w plane to see how to kind of study the nature or the properties of our mapping. We did this example where we looked at w equals z squared, and we looked at how w equals z squared maps constant lines u equals 2, 1, -1, and 2. And also we looked at how it maps constant lines v equals 1, 2, -1, -1 and -2. We see algebraically that when we looked at w equals z squared, we substituted x plus iy and then squared it. And then we found our u function, the real part, is equal to x squared minus y squared, and our imaginary part was equal to 2xy. When we set u equal to a constant, we get a hyperbola. When we set v equal to a constant, we also get a hyperbola. And then we can go ahead and graph it. I don't know, you can use Wolfram Alpha. I didn't, I just kind of used these guidelines, and I knew where the intersection on the axis would be, and then I mapped the u, the constant u's, to these hyperbolas. I mapped the constant v's to these hyperbolas. We also did note that the u and v lines in the w plane intersect at 90-degree angles. Here, when we intersect these hyperbola with these hyperbolas, theoretically, they should also intersect at 90-degree angles, and they do. Anything in the drawing that appears off, it's due to my drawing ability or lack thereof. Finally, we defined what a conformal map is, and a mapping function is said to be conformal if it preserves angles. That is, a conformal map will map two lines that intersect at some angle into another pair of lines that intersect at the same angle. And we also have this fact here: all complex functions which are analytic are conformal mapping functions. And then we did an example that sort of illustrated all three concepts of the mapping of a function, the use of the grid lines, and also the conformal maps, and we verified that our angles were preserved. So that's it for this video. Thank you for watching.